Welcome back to Dead Reckoning, the Human Life Expectancy channel. This is the second of 4 videos on traditional technologies that could impact human life expectancy in the future, and will focus on clean water. Water is the source of all life on Earth, and access to clean water is essential for human survival. Unfortunately, clean drinking water is becoming increasingly scarce. While 71% of the Earth's surface is covered in water, only 2.5% of global water is fresh, and because most of that is frozen into ice and glaciers, only 1% is available for human use in lakes, rivers, and underground. Since 1900, the human population's dramatic growth has more than quintupled the demand for water, putting a squeeze on this critical resource. As a result, many countries are experiencing high levels of water stress. Making matters worse, climate change is melting ice, reducing the supply of fresh water and creating new deserts while simultaneously increasing the severity of rainstorms. In Asia, over 1.5 billion people depend on water from melting glaciers in the Himalayas. But a recent study estimates that 2/3 of these glaciers will be gone by 2100. In response, farmers and societies have placed unprecedented demands on underground aquifers, which are now in steep decline. In 2017, 29% of the global population lacked access to safely managed drinking water. In addition, in 2019, almost 6% of global yearly deaths were caused by waterborne diseases. These deaths fell disproportionately on the poor. The UN expects that 14% of the world's population will encounter water scarcity by 2025. These facts make the discussion of water inextricable from our conversation about forecast human life expectancy. Some governments around the world are undertaking efforts to increase the supply by using rivers and dams, capturing rainwater, reclaiming wastewater, and using new technologies to produce water. Others are responding with efforts to reduce demand by instituting limits and increasing water pricing so that water is not treated as a commodity or wasted. Globally, approximately 70% of water is used for agriculture. 19% is used for industry and 11% is used for municipal or domestic uses. However, this share varies significantly by country based on wealth, climate, and other factors. The average agricultural water use for low-income countries is up to 90%, 79% for middle-income, and only 41% at high-income countries. Since so much water is used in agriculture, efforts to use it more efficiently are key to ensuring enough water for all. Initiatives include producing less food that's water inefficient. A good first step would be to produce less meat. Meat is extremely water inefficient to produce. For example, a kilogram of beef takes up to 15 tons of water to produce, while it takes only 1 to 3 tons of water to grow 1 kilogram of cereal. This also highlights the importance of vegetarianism and limiting food waste, as we'll discuss in our next video on life-extending food technologies. There are also multiple initiatives we can undertake to use water more efficiently in agriculture, including efficient irrigation versus flood irrigation and vertical farming. You can also use cover crops or tillage management or no-till farming techniques. There's also much we can do to improve water governance. Promoting international trade, which allows crops to be produced more efficiently. Reducing domestic support initiatives. We can also improve water sustainability by removing incentives to overuse water and creating incentives to promote efficient water use. We can also improve water supply management by capturing rainwater and reducing storm runoff. Technology can also play an important role. Fortunately, most of the illnesses and deaths associated with water can be prevented through measures provided by clean water technologies, such as boiling, filtration, distillation, chlorination, sedimentation, and oxidation. Even better, since energy is the primary limiting factor in these technologies, as energy becomes less expensive and more carbon neutral, clean water can be made available to those in need. 3 new clean water technologies are poised to increase access to clean water and extend HLE. The first technology is water filtration. Today, filters use sieving, absorption, ion exchanges, biofilms, and other processes to remove harmful chemicals, bacteria, protozoa, and microbial cysts from water. However, water filtration can involve a lot of energy to force water through the filters, and the filters may have fine meshes that must be replaced or cleaned, or ceramic surfaces that must be abraded when they've become clogged with impurities. Today, nanotechnology increasingly allows us to manipulate materials on an atomic scale, allowing us to make filters that are larger, stronger, and more durable. Also, by changing the electrical, optical, physical, chemical, or biological properties at the nano level, we can filter out harmful chemicals and biological agents with great precision. Filtration is used to reclaim municipal wastewater or sewage, industrial wastewater or stormwater runoff, and turn it into water that can be reused for urban, agricultural, environmental, or even planned potable applications. For example, water can be reclaimed for the irrigation of agricultural fields, lawns, and gardens in cities, or replenishing surface water and groundwater. Water can also be reused for residential applications such as toilet flushing, and can even be treated to reach drinking water standards. However, drinking reclaimed water is not yet common. Currently, the cost of reclaimed water exceeds the cost of potable water in many regions of the world, where a freshwater supply is plentiful. However, water recycling and reuse is of increasing importance, not only in arid regions such as the Middle East and North Africa, but also in cities and contaminated environments. Another technology for generating water is atmospheric water generators. Atmospheric water generations extract water from humid, ambient air. There's almost always a small amount of water in the air that can be extracted. Historically, atmospheric water generation methods were completely passive, requiring no external energy source and relying solely on temperature variations. For example, from the 12th to the 19th centuries, the Incas were able to sustain their culture above the rain line with water-collecting fog fences. Today, one type of atmospheric water generation called source uses a solar panel to power a fan which draws in ambient air and pushes it through a hygroscopic, water-absorbing material that traps water vapor from the air. The water vapor is extracted and passively condenses into liquid that's collected in the reservoir. Finally, minerals are added to make the water ready to drink. This off-grid solution can work even in high-temperature, low-humidity environments such as deserts. Other atmospheric water generations use energy to extract water vapor by cooling air below its dew point or exposing it to desiccants. However, this too requires a lot of energy. When powered by coal-based electricity, it has one of the worst carbon footprints of any water source, over 1,000 times more than reverse osmosis seawater desalination, which we'll cover in just a minute. And it demands more than 4 times as much water up the supply chain than it delivers to the user. So this makes it suitable for local and temporary water supply only. The third technology is water desalination, and it's poised to provide mankind with much more water. In many places where there's a lack of available drinking water, there is ample salt water. In these places, seawater can be desalinated by removing salt and other minerals, making it suitable for human consumption. In many places, desalination is now a cost-effective way to provide fresh water for human use. There are approximately 16,000 operational desalination plants located across 177 countries, which generate an estimated 95 million cubic meters per day of fresh water, accounting for about 1% of the world's drinking water. Desalination is particularly prevalent in countries located in the Middle East and the North Africa region, such as Saudi Arabia, UAE, Kuwait, and Egypt, which has just announced 17 new plants. Desalination is also an important source of water in small island developing states. Desalination is also used on many seagoing ships and submarines. The leading process for desalination in terms of installed capacity and yearly growth is reverse osmosis. This process forces water through semi-permeable membranes while rejecting salts. New filters made through a process called coaxial electrospinning, where an electric force is used to draw charged nanofibers of 2 different materials out of nozzles, offers up to a 99.99% efficiency. However, the energy costs in the desalination process are high, but vary considerably depending upon the water salinity, plant size, and process type. Reverse osmosis can also have negative environmental impacts. The byproduct of the desalination process is brine, which can harm the local aquatic environment if it's not released properly. The dense, heavy brine is sometimes referred to as the blanket of death because it settles on the seafloor, killing most sea life. If the energy comes from coal or other dirty sources, desalination can paradoxically create more global warming, giving rise to even greater need for desalination. Today, in most regions, due to its energy consumption, desalinating seawater is generally more costly than fresh water from surface water or groundwater, water recycling, or water conservation. However, these alternatives are not always available, and depletion of reserves is a critical problem worldwide. At present, the cost of seawater desalination is higher than traditional water sources, but it is expected that the cost will continue to decrease with technology improvements and reduced energy costs. One recent study showed that desalination processes can be enhanced to extract valuable lithium, hydrogen, and chlorine gas, adding to its economic viability. Increased demand for clean water, combined with anticipated improvements in efficiency and reductions in costs, all but guarantee that desalination will increasingly be relied upon to deliver an almost limitless amount of clean water for human consumption. So, in sum, how might water technologies impact future HLE? We must start to use water more efficiently and employ new technologies to ensure clean water for all of us. The impacts of water filtration and desalination technologies on our health are so large that different assumptions about the type and rates of innovations drive different levels of HLE. Based on our research and advice of experts, we formed different assumptions and incorporated them into the scenarios that were used to determine our forecast HLE. In our next video, we'll explore potential impacts of new food technologies on HLE. In the meantime, please hit the like button below, subscribe to the Human Life Expectancy channel to make sure you don't miss our next videos, and post comments for the topics you'd like to have us cover. Thanks for joining us. And until next time, as we say at Human Life Expectancy Inc., Hi Hua! Do what you can to help yourself and to help us all to live longer.